In our examples, P represents a proposition. In fact, P can also represent a series of propositions. We call them premises or what we know. On the other hand, we have Q of propositions or a series of propositions too, to which we call conclusion or what we want to know. People may have P as follows as premises. People who routinely do morning exercise have a good endurance, and I routinely do morning exercise. So the logical conclusion would be I have a good endurance. In math, we may have similar situations. For instance, we have premises x equals 5, and the logical conclusion is x squared minus 4x minus 5 equals 0. Is the conclusion correct, or is it a true implication? Can it be replaced with equivalence? To answer the questions, we need the so-called mathematical proof. So, we may recall our logical operations to provide a mathematical proof. Remember the first indication for correct implication. If P is true, then Q must be true. With this in mind, we may provide the mathematical proof by simply starting with the premises P and successfully working forward to the conclusions Q. This simple but straightforward method is called direct proof. Our case here is easy. Since P x equals 5 is true, inserting x equals 5 to the conclusions or Q, we get x squared minus 4x minus 5 equals 0. So obviously the conclusion is also true. Therefore, we can conclude that P implies Q is correct by direct proof. Another way to provide the mathematical proof is using the so-called indirect proof or proof by contrapositive. Remember in our previous discussion, with correct implications of P to Q, Q is a necessary conditions for P. It requires that if Q is not satisfied, neither must be P. This is what we call contrapositive. So in our case, the contrapositive of P implies Q statement is this. Then we know by factoring, we can get this for true Q, so that Q could have two possible values, either 5 or minus 1. But since the contrapositive requires us to have the otherwise, so the possible values for x are all numbers other than 5 and minus 1. Does it imply x doesn't equal 5? Indeed it does. So again, P implies Q is a correct implications, but now by indirect proof or proof by contrapositive. Proof by contradiction is the third way to provide the mathematical proof. Recall again that a proposition is an assertion that is either true or false, but not both. So if proposition P implies Q is true, then P implies not Q, or the contradiction must be false. Proof by contradiction is therefore a way to prove that the contradictions cannot be right. In our example, P implies not Q means that Q equals 5 implies x squared minus 4x minus 5 is not equal to 0. From direct proof earlier, we know that there is no way that x squared minus 4x minus 5 is not equal to 0 when x equals 5. So this contradiction cannot be right. It's false. In other words, since the contradiction cannot be right, we can conclude that the implication again is true. As for proof by induction, basically the method is used to verify formulas involving natural numbers. I will let you try it from examples in the textbook or other resources, but at the moment you may try to find out why we don't use proof by induction method to verify our case. After providing mathematical proofs that P implies Q is true implications, can the implication arrow in our statement be replaced with equivalence arrow? In this case, the answer is no, because to have equivalence condition, P must imply Q, but at the same time, Q must also imply P. Yes, P implies Q in our case, but Q, however, doesn't imply P, because to satisfy Q, x equals 5 is not the only solution, but also x equals minus 1. Before closing the video, I would like to explain to you a little bit just briefly about the subject basic math. Why is math important in learning economics and business? What you have to notice first is that math is a tool in learning economics and business. And just like in any other subject, math helps us understand and verify the construction and the reasoning of a specific theory. Moreover, math itself can be used to construct a theory from a given set of assumptions or postulates via a process of reasoning. With math, the statements of assumption and conclusion can be huge and represented more concisely and precisely with the symbols and matrices. The process of reasoning may also be very much helped with a wealth of mathematical theorems. Using math, the assumption is stated explicitly so that the validity of a certain theory can be more accurately verified. And the last advantage of mathematical process is that it allows us to deal with an variable case. Okay, so I think that's all from me. You can continue to the Eureka sessions, the exercise. So see you. Assalamualaikum warahmatullahi wabarakatuh.